Hello all. So now what we do is, in the last video we studied about the elements of embedded systems. Now we will study it in depth. So first one is core of an embedded system. Embedded systems are domain and application specific, right? So normally the embedded systems are considered as two types. One is domain specific, second one is application specific, and built around a central core. Built around a central core, right? The core of an embedded system falls into any one of the following categories. So these are the four categories across which the core of an embedded system will fall into. The first one is general purpose and domain specific, right? So in this we are having microprocessors, microcontrollers, and digital signal processors are the examples for general purpose and domain specific, right? And the second one is application specific integrated circuits, that is ASICs. Third one is programmable logical devices, that is PLDs. The last one is commercial off the shelf components, that is COTS. Commercial off the shelf components, that is nothing but COTS. Correct? So when we are studying this, we should know the difference between microprocessors and microcontrollers. So what is a microprocessor? Microprocessor is nothing but a silicon chip representing a central processing unit, CPU, which is capable of performing the arithmetic as well as logical operations according to a predefined set of instructions. That means what? This microprocessor is having only one part, that is nothing but a CPU, that is nothing but a central processing unit, right? It will be having only one part, that is nothing but a central processing unit. Whereas this microcontroller is a highly integrated chip that contains CPU and then RAM and then ROM, and then flash memory, and then it will be having IO ports. So integration of everything is nothing but a controller, and only CPU is nothing but microprocessor. It is an independent unit. It requires the combination of other chips like timers, program, memory chips, and then for the functioning, right? But it is a self-contained unit. It doesn't require anything. Everything will be inbuilt. Like timer, UART, etc. will be inbuilt. Most of the time, the general purpose, it is in design and operation, right? So mostly application oriented for domain specific, right? So normally these microprocessors are considered as general purpose, whereas these microcontrollers are considered as application specific. Doesn't contain a built-in IO port, and the IO port functionality needs to be implemented with the help of external programmable peripherals such as 8255, right? So that means what? We need to connect 8255 chip so that it becomes it acts as an IO port for microprocessor. Whereas over here, most of the processors contain inbuilt IO port, which is nothing but it can be either 8, 16 or 32-bit. Targeted for high-end market where performance is important, targeted for embedded market where performance is not so critical. Limited power saving options will be there, whereas over in microcontroller there is lots of power saving options are available. The next one is RISC versus CISC. So in the RISC versus CISC, so there are less number of instructions are there are greater number of instructions are there in CISC. Instruction pipelining and increased execution speed, right? So there is instruction pipelining and increased execution speed is there in RISC. Whereas over here, there is no instruction pipelining feature is there. So this is the greatest disadvantage of RISC. There is no pipelining option, right? The orthogonal instruction set allows each instruction, there is an orthogonal instruction set, which allows each instruction to operate on any register and use of any addressing mode, in RISC. Whereas over here, there is a non-orthogonal instruction set is there. Operations are performed on registers only, whereas over here, operations are performed on registers, memory, depending on the type of instruction. Large number of register sets are available. Over here, general purpose register sets are available. Programmer needs to write more code to execute a task since the instructions are very simpler ones. Whereas over here, programmer can write a complex instruction so that he can reduce the density of the code. Single fixed length instructions are there. There is variable length instructions are there. Less silicon usage. Over here there is more silicon usage is there. With Harvard architecture is there. Over here, Harvard or von Neumann architecture can be used in CISC processors. Over here we are having Harvard versus von Neumann architecture. So in a Harvard architecture, as you can see, there are separate buses for instruction and data fetching. Over here, there is a single bus is there. You can see over here, there is a single bus is there for instruction fetch and data fetch. Easier to pipeline, so high performance can be achieved. Okay, over here low performance compared to a Harvard architecture. Why? Because pipelining feature over here, okay, it's very difficult because there is only single bus over here. Comparatively high cost, whereas over here it is cheaper. Okay, no memory alignment problems are there. Over here there is it allows self-modifying codes. Since the data memory and the program memory are stored physically in different address locations, so no chances of accidental corruption over here. Whereas over here the data memory and program memory are the same chip, so the chances of accidental corruption of program memory will be there. Okay. The next concept is in the general purpose and domain specific. It is big Endian versus little Endian process, right? Endianness specifies the order in which the data is stored in the memory, okay, by the processor, okay, operations in a multi-byte systems. Okay. For example, the higher order data byte, okay, in higher memory location, and the lower order data byte is the lower location just below the higher memory. Then it is called as, okay, big Endian. Right. So lower data byte at the higher memory location and higher data byte at the lower location just below the higher memory. Okay, it has been explained over here. You can find out that there is a little Endian over here. So what is that? The lower data byte is stored in what? The lower address, lower memory, whereas the higher byte is stored in a higher memory location. Okay, that's what is little Endian. Whereas over here in the big Endian, the lower data, that is the LSB of the data, is stored in a higher memory location, whereas the MSB of the data is stored in a lower memory location. Okay, so this is what the big Endian and little Endian means. So again we are having RISC processor, okay, load, store, operations and all. So, okay, so the memory access related operations are performed by the special instructions called as load and store. If the operand or data is specified as a memory location, okay, the content of the loaded is to a register using the load instruction, and the instruction stores the data from a specified register to a memory location. Okay, this is how the load, store instructions have been defined. Then the second part is application specific integrated circuits, that is nothing but ASICs. Okay. Microchip designed for a specific or unique application. Okay, so it is, what is ASIC? It is a microchip designed for a specific or unique application, used as a replacement or to a conventional general purpose logic chips. It consumes a very small area in the total system. That's what is ASIC mean. Helps to design a smaller systems with high capabilities and functionalities. It integrates several functions into a single chip by reducing the system development cost. Most of the ASICs are proprietary products. That means they have been owned by some of the companies. Then the third one is PLDs. Okay, what is PLD? Programmable logic devices. What is PLDs? Programmable logic devices. The logic devices provide functions including device to device interfacing, data communication, signal processing, data display, timing and control operations. Logic devices are classified into two broad categories, okay, that are fixed and programmable. What do you know fixed? Fixed is nothing but permanent, perform one function or set of functions, right? So PLDs are nothing but fixed. Logical devices are fixed but perform one or set of functions. Once manufactured, cannot be changed at all. That's what is logical devices mean. Okay, once if the programmable logical devices are manufactured, they cannot be changed at all. What do you mean by programmable logic devices? Programmable logic devices are nothing but offers customers a wide range of features. Okay, the logic capacity, they are having a higher logic capacity with a very high speed and voltage, having a good voltage characteristics. They are reconfigurable for any number of times. Then the next one is the commercial off-the-shelf components, that is nothing but COTS. These are designed to provide us easy integration and interoperability with the existing system components, right? The COTS component itself may be developed with the following: a general purpose, an application specific integrated circuit and a programmable logic device. Typical examples, okay, the car toy remote controller, for example, that will be having a RF circuitry and then it will be having a high performance, high frequency microwave electronics, okay, which is around 200 gigahertz. It will be having high bandwidth ADCs and then devices and components operating at a very high temperature. Okay, these are having electro-optic HR imaging arrays also, and then they will be having UV or IR detectors also. Okay. The other example are TCP ICP plug-in mobile like Viznet, Freescale, Dynalog, etc. Okay. So this is the core of an embedded system means. Okay. So in the next video, we are going to study the further part of the module 3. Okay. So thank you.